Okay, so this is the problem that we want to solve here. The new thing, in addition to it being a quasi-linear equation, is that we have a non-zero thing on the right-hand side. So, as I have been doing, I just like to start drawing the axes here for the characteristics, just because that's how I like to think about things. Okay, so setting up as usual. We can parameterize the the x-axis, and this way, that's our curve, x is equal to 0, or sorry, t is equal to 0. We're going to have t prime of s is equal to 1, with t of 0 is equal to 0. X prime of s is going to be equal to z of s, with x of 0 equal to x naught. Okay, remember z of s is u of x of s, u of x of s, t of s. And now z prime of s is going to be equal to z of s. Okay, and then z of 0. Remember, z of 0 is just this function evaluated at that point, or that point. Okay, so this is going to be equal to 1 if x naught is less than 0, and 2 if x naught is greater than 0. And again, we're going to leave it ambiguous as to what happens when x naught is equal to 0. This will be a little bit different than the problems, than the first two problems that we've seen, kind of structurally. You'll see what I mean. Sorry, I need to grab my marker. Okay, so let's look at a characteristic that starts over here at this x naught. So here, x naught is bigger than 0. So if I look at z of s, so z prime is equal to z. So this tells me on a characteristic that starts at this point x naught, z of s is going to be equal to 2 times e to the s. 2 times e to the s. Okay. Furthermore, t of s is equal to s. And then x of s, well, x prime of s is equal to 2e to the s. X prime of s is equal to 2e to the s. So now this tells us that x of s, well, x of s is going to be equal to 2e to the s plus some constant. Sorry, I said plus some constant, but I wrote x naught. So plus some constant. Okay, so let's figure out what that constant is. It's a characteristic that starts at this point right here. So when s is equal to 0, x of s should be equal to x naught. Okay, so we're going to have x naught is equal to 2 plus c. So c is equal to x naught minus 2. So c is equal to x naught minus 2. So it's going to be plus x naught minus 2. Okay, and so these are going to be the characteristics over here. Now, I want to draw them. I want to be able to sketch the characteristics. And for me, when I'm sketching a characteristic, it's easier if I think about it as the graph of a function. So here, s is equal to t, so I can think about this as x equals 2e to the t plus x naught minus 2. So I've got x is equal to 2e to the t plus x naught minus 2. And now what I can do is I can solve this for t in terms of x. So I'm going to add 2 to both sides, or sorry, it's going to be x plus 2 minus x naught divided by 2. And I'm going to take the natural log of that. So what I have, it's log of x plus 2 minus x naught plus 2. Let's see, I can write this 2 minus x naught. I can write this as minus x naught plus 2. So let me just make sure I did that correctly. No, x minus 2. It's plus 2 minus x naught. Sorry, this is embarrassing. Let me go back to what I had before. So it's gonna be x plus 2 minus x naught over 2, and we're going to do log of this, and I can write that as minus x naught minus 2. Okay, minus x naught minus 2. Okay, so in other words, it's going to be the log function, but shifted over shifted over by x minus 2, shifted to the right by x minus 2. All right, sorry for that interruption. I guess it's probably not a very long interruption in the video since I paused it there. Okay, so now I want to see what happens. So again, this is technically just for x naught greater than 0, but I want to see what happens at x naught equals 0. So if x naught is equal to 0, this becomes, I'm just going to write it down here, it's log of x plus 2 over 2. So minus 2 gives me plus 2, and this, by the properties of logarithms, is just log of x plus 2 minus log of 2. Okay. Sorry, there's loud noise. All right, log of x plus 2 minus log of x minus log of 2. This is for x not equal to 0. This is when I'm starting at this point here. All right, I think that was the last of the interruptions. Okay, so now this is just going to be a logarithmic function. I'm not going to worry about sketching it exactly, but we know what the general shape of it is. When x is equal to 0, obviously we're going to be here. That's what the x naught being equal to 0 means. And then it's just going to be, log of x plus 2. This is going to be this standard logarithmic function shifted to the left, and then minus log 2 shifted down, so it kind of crosses through the origin here. But as usual, I'm going to do this with a dashed line. So log of x plus 2 minus 2. Minus log 2. I guess I'm going to need to, okay. So what that shows us, so now sorry. Okay, so now let me just remind you what I had over here. T is equal to log of, x minus x naught minus 2 over 2, and then on these characteristics, z of s is equal to 2e to the s. I guess I can just look at the problem over there, 2e to the s. Okay, sorry, let me just make sure that everything is how I need it to be. All right. And I guess let me point out, it's going to be important in just a moment here. The derivative, if I look at the derivative of this, like if I look at the derivative of this function, when x is equal to 0, like if you do the derivative of this, when x is equal to 0, you can look right here, it's going to be 1 over x plus 2, which is equal to 1/2. So the slope here is equal to 1/2. So I'm just going to record that because it's going to help me when I draw the blue characteristics, which are going to be the characteristics to the left. And then, of course, any, whatever x naught here is just going to be this shifted to the right more. So I'm going to have a characteristic that looks like this over here. Okay, now let's look at the characteristics over here on the left-hand side. So I'll look at this generic value of x naught here. All right, and now I know z of s, well, z prime is still equal to z, but now z of 0 is equal to 1. So z of s is just going to be equal to e to the s. And we know if we look at the equation for t, it says t prime is equal to 1 with t of 0 equals 0. So T of S is equal to e to the t. Now you can do a similar procedure, as I did over here, to figure out how to write t as a function of x. But we can do what we're about to do anyway, and what we learned before. We could say, okay, the derivative of these characteristics is going to be 1 over u, but u along the characteristics is e to the s, and that's equal to t. So t prime of x is equal to 1 over e to the t, or this is equal to e to the minus t. Now remember, t is a function of x. So we have a very strange differential equation here. T prime equals e to the minus t. So let's see, how do we want to solve this? Well, we can think about dt as being dt dx. So we've got dt. I actually know what the solution is, and I wasn't planning on solving it, but I'll just go ahead and solve it. So we've got dt over dx equals e to the minus t. If I multiply e to the t to both sides, it's e to the t dt equals dx. If I anti-differentiate over here, I get e to the t. If I anti-differentiate over here, I'm going to get x plus c like this. Okay, and so now what this tells me, if I take logarithms of both sides, this tells me that t of x is going to be natural log of x plus c. So natural log of x plus c. And then when t is equal to 0, x is equal to x naught, and so we have 0 is equal to log of x naught plus c. Okay, so if 0 is equal to log of x naught plus c, this means x naught plus c is equal to 1. X naught plus c equals 1, so the argument to log has to be equal to 1. X naught plus 1 is equal to c, so c is equal to 1 minus x naught. So c is equal to 1 minus x naught. So I can write this c as 1 minus x naught, or I could write it as 1 minus x naught or minus x naught minus 1, like this. Okay, and then you can tell that if x is equal to x naught, we have x naught minus x naught, and then a minus 1, or minus minus 1, so that's log. Okay, so let me write this then a little bit cleaner. Z of s is equal to e to the s, and then, excuse me, t of x is equal to log of x minus x naught minus 1, and then t of s is equal to x. These are all different ways of kind of writing, or these are all sort of mixing ways of writing these equations. All right. And again, we could have solved the equations like we did over here for x of s and gotten x of s as some exponential function, and then solved for t in terms of x like this. But what we have here is fine for what we're doing. Okay, so now again, this is only supposed to make sense for x naught bigger x naught less than 0, but the limiting case is going to be when x naught is equal to 0. If x naught is equal to 0, this is log of x plus 1. So if x naught is greater than 0, if x naught is equal to 0, this becomes log of x plus 1. Okay, it's log of x plus 1. And notice the derivative of log of x plus 1 is 1 over x. When x is equal to 0, that's 1. So the derivative here is going to be bigger. So we're going to have a characteristic that's above this one. Okay, but they're both going to cross at this point. So we're going to have this. And let me just remind you, this curve, this purple dashed line is t equals log of x plus 2 over 2, and this is t is equal to log of x plus 1. Okay. All right, so now if I look, we've got characteristics that are going over here like this. Okay, so now if I pick a point here, and I call that x comma t, that point is xt. For this point here, it lies on this characteristic, it's going to be z of s is equal to e to the s, but notice it doesn't depend on the x naught value, it's just e to the s right here. And s is equal to t. So u is equal to e to the t over here. And similarly, we have u equals e to the 2t over here. Kind of weird, but let's see if it's going to satisfy this differential equation. If I take the t derivative of u, that's e to the t. The x derivative of u over here, blue, is going to be 0 because there's no x's. And so the t derivative is e to t, e to the t. E to the t is equal to u, so that equals u. And something similar can be said for the blue curves. On top of that, if you plug in t is equal to 0, u of 0 is equal to 1, and if you plug in t equals 0 over here, u of, if t is equal to 0, you get 2. So the blue curves and the purple curves both satisfy the PDE. Now, of course, we have these characteristics in between. Now, I want to point out something here. The slope of the purple characteristics is 1/2. That's 1 over this value. This is 1. And so again, what we're saying is that all of the slopes between 1/2 and 1 must exist there. So there's a characteristic for each slope that goes through that line there. So let me now erase. It's going to be a little bit different than what we saw before. Sorry, let me look at my notes to see exactly how I had this. So if we look at these two different things here, we can kind of think about the blue curve as being well, they both have the following form. T equals log of x minus something. I'm going to call it x minus x naught minus a divided by a, where here, the blue curve here, hold on one second. Sorry, my computer screen keeps making it seem like there's something going wrong with the Camtasia recording. Anyways, they both have this format here. Sorry, this should be an A. And now where x naught is equal to 0. So this kind of is the generic form of the characteristics both over here and over here. But the blue and purple characteristics have the specific form of this t minus log. T is equal to log of x minus a over a. I really need a break here. And this is for a going between 1 and 2. So now our characteristics, we want to look at characteristics like that for a going between 1 and 2. Okay, so we're going to look at a characteristic like this. It's going to look like that for a particular value of a. I can write this in the following form: log of x minus a minus log of a, and that'll make it a little more clear what we're going to want to do here. And now we're just going to do exactly what we've been doing before, which is to say t prime of x is going to be 1 over that, 1 over u. Okay, and then we want to solve for u. Okay, so t prime of x, we're going to have 1 over x minus a. So t prime of x is going to be 1 over x minus a. And then we're going to say this is equal to 1 over u. So in other words, in this region here, u is equal to 1. Sorry, u is equal to x minus a. So I'm gonna write that now. So u is equal to x minus a. All right. So there's a number of ways we can now work through this. Notice I have this equation. I want to write a in terms of x or t. So that's sort of what I want to go for here. So how can I do this? Well, if I look at this equation right here, maybe the easiest thing is just to exponentiate both sides. And on the left-hand side, I'm going to have e to the t. And on the right-hand side, I'm going to have x minus a over a. Again, my goal here is to solve this equation for a. So whatever method you want to do, that's fine. I'm going to multiply both sides by a and then add a. So we get a times 1 plus, a. There's a storm coming, so windows and things are cracking, which is always a little nerve-wracking. So this is equal to x, and now we see a is equal to x over 1 plus e to the t. So this is 1 over 1 plus e to the t. So in this range right here, this is what u is equal to. Okay. Okay, and yes, sorry. I thought there was a mistake here, so I checked my notes here, yes. So I had, just to recap, there was a mistake here. If you want to solve this for a, you have e to the t is equal to x minus a over a. When I moved everything over, I just forgot about the 1 when I divided by the 1 plus e to the t. Anyways, this is the solution. I think it's probably more helpful to write it as x times e to the t over, x times e to the t over 1 plus e to the t. And the reason I say that is because I want you to verify that it satisfies this equation, and I think that's a little bit easier to work with than this. I don't know, maybe you agree, maybe you disagree. Okay, the last thing that I want to think about here, if we think about the characteristics one more time, so we could either, well, let's do it this way. Let me sort of do it the way that I feel like I can get to the quickest. If I look at this blue equation, if I solve that for, let's say, x in terms of t, I'm going to exponentiate both sides to get e to the t equals x plus 1. So this says x is equal to e to the t minus 1, like this. And now over here, if I say on the purple curve, if I say what happens if I raise both sides to the power, if I raise e to the power of both sides, is going to be e to the t is equal to x plus 2 over 2. So 2 e to the t minus 2 is equal to x. Okay, now if that's what I am wanting you to do here is I'm wanting you to see what the value of the solution is along the purple characteristic. Okay, like if you just take u equals e to the 2t and you plug in t is equal to this, maybe I didn't even need to do this part. See if it's equal to the black characteristic corresponding to whatever value a would need to correspond to, I guess in that case 2. See if they're equal to each other. In other words, see whether or not our solution is continuous on these dotted lines, or those dashed curves there. Okay, sorry about that. I had a couple of technical issues, and then at the end there had a little confusion with the solution that I got because I made a mistake without that, by that x there. That's it for this problem. Just another example that's not in the book and that is not a homework problem either that I wanted to show you guys, just for practice. And of course, for the homework problems, I'll be posting solutions.